Hello, my name is Robin Cleveland. I'm at the Institute of Biomedical Engineering at the University of Oxford, and I will be giving you a ThUNDDAR talk on ultrasound propagation, the fundamentals, and this is the first in the series of ThUNDDAR live talks that are taking place in 2020. So the motivation for this is looking at how therapeutic ultrasound, the physics behind the therapeutic ultrasound, and this slide kind of gives a motivation for the effects that we need, that we're going to be interested in. Typically in therapeutic ultrasound, the therapeutic ultrasound transducer is placed outside of the body. There'll be some sort of coupling media, typically water, sometimes a gel, some gel pad, that will, for which the sound will travel through before it enters into the body. And then as it enters in and propagates through the body, it has to pass through layers of skin, some intervening tissue, often layers of fat and muscle, and then into the organ of interest where the treatment is desired to take place. The transducer is normally focused, so we get a focusing beam effect going in here, and then in the treatment site where we have the highest intensity region is where we get the bioeffects. And so the physics that go into this propagation effect, so we have reflection and refraction as we go from the water into different layers of tissue. Different changes in the impedance and the sound speed will mean that the wave gets refracted and aberrated. Typically, because we are interested in focusing, so we have a focusing effects to worry about, and in particular the region around the focal spot is the size of that, and the distribution that is governed by diffraction. Tissue is not homogeneous, and so we have aberration and scattering effects. So for example, the sound speed in fat tends to be quite lower than most other soft tissues, and that can lead to aberration effects. And the range of length scales of all the different organs going all the way down to cells inside the body result in scattering. The body's not lossless. Some of the energy from the sound wave is absorbed, and that effect needs to be accounted for. And then finally, for the sort of intensities that are normally used in therapeutic ultrasound, the amplitudes are very high. And so linear acoustics is not always the best descriptor, and we need to worry about nonlinear effects. The motivation for doing this is to see what bioeffects we get in the tissue. The most common ones that are apparent in therapeutic ultrasound are thermal. So the absorption of the sound wave by the tissue results in tissue heating. And so understanding that temperature rise and what the acoustic effects play a role is important. And the second one is mechanical, and cavitation is the main player in that case. And there it's actually the negative pressure that will make cavities grow and make them grow, and then positive pressures can make them collapse. And so in order for us to understand the bioeffects in tissue that we get from therapeutic ultrasound, we need to understand both how energy is deposited in terms of heating, but also what the pressure waveforms are in order to determine cavitation effects. And so the goal of these lectures is to give you the first kind of introductory to the physics that plays a role in determining those. Right, so the outline, so there are many effects in there. In this first talk, I'm not going to be able to get through everything, so I will give you a basic introduction into the acoustic wave equation, discuss the ideas of impedance and intensity, and then we'll look at reflection, refraction, and how impedance plays a role in those as we go from one medium to a next. With subsequent talks, I will try and cover the other topics that are listed on this outline slide. So just as a bit of background, hopefully most of you know from your high school physics that sound is a longitudinal wave. The little cartoon here from the Institute of Sound and Vibration in Southampton kind of shows a piston driving a gas in a tube. And you can see that the piston compresses the gas here, and then that compression moves down the tube. And so we have this compression and rarefaction, and the motion of the particles is in the same direction as which the wave is traveling, which makes it a longitudinal wave. Now notice that even though we have energy being transmitted or information being transmitted down the tube, the particles themselves don't actually undergo any net bulk motion. So the little red dots here are tracking individual fluid particles. And you can see that that red dot moves backwards and forwards, but actually doesn't go down the tube. And so with acoustic waves, we have transmission of energy and information, but without actually bulk transmission of the wave. Now, in many cases in acoustics, we consider sine waves. They have some very nice mathematical properties that make it easy to analyze. And again, that's probably what you will have seen in high school physics. And kind of the three important physical properties to do with a sound wave, or any wave. First is the wavelength, so that's the distance in meters from the 2 points of the same phase on a wave, for example, 2 peaks. or two troughs, or if you go from one zero crossing to another zero crossing, all of those will give you the wavelength, and that's typically given the Greek symbol lambda. The other one is the frequency, so that's how many cycles per second we have, typically again measured in hertz, and then the period, which is the duration of one cycle in seconds. And so from high school physics, you should have recall these equations here. The wavelength is equal to the speed of sound times the period, or it's the speed of sound divided by the frequency. And so for water and for tissue and water have similar acoustic properties in many ways. The speed of sound is roughly 1,500 meters a second. And we often in biomedical ultrasound, we talk about that as 1.5 millimeters per microsecond. We're typically interested in millimeter length scales. And so it turns out to be convenient to think about microsecond timescales as well. So what does that mean? So again, biomedical ultrasound frequencies are on the order of megahertz. Ultrasound itself is defined as any frequency above 20 kilohertz, which is the edge of normal hearing. But actually in biomedical ultrasound, it normally is in the megahertz regime. And so for a frequency of 1 megahertz, that gives you a period of 1 microsecond and a wavelength in either water and tissue of about 1.5 millimeters. Right, and those, if you're working biomedical ultrasound, those are good numbers to have at the tip of your fingers. 1.5 millimeters per microsecond, and wavelengths on the order of 1.5 millimeters for 1 megahertz. And so when we do stuff to do with ultrasound, we will treat ultrasound in the body as a longitudinal wave. Now, in reality, there are shear waves in the tissue. Tissue isn't a perfect fluid, or it's not a fluid. It's more complex than that. But the shear waves tend to only be important at kilohertz frequencies and lower. And so for what we'll be doing, what I'll be talking about here, I'm going to treat the tissue in the body at megahertz frequencies as a simple fluid, and we'll only worry about the longitudinal wave components. As I mentioned, there are shear wave components, but that's beyond the scope of what I'm going to be talking about. So what are the underlying physics then that govern what happens for a sound wave? So if we can treat the body as a fluid from the point of view of a biomedical ultrasound, then the fluid dynamics equations are what sits behind the physics. Many of you will have seen fluid dynamics equations if you've done mechanical engineering or physics at university. What's different when we do acoustics is that in most fluid dynamics equations, a common assumption is what's referred to as the incompressible assumption. That is that the density of the fluid doesn't change. And for flows that are much less than the speed of sound, that's quite a reasonable assumption. But in this case, where we do actually have disturbances moving at the speed of sound, we can't make that assumption anymore. And so our basic equations are conservation of mass, also known as the continuity equation. And when density does vary, then we can't get rid of the density terms. And so this becomes our conservation of mass equation. The second one is conservation of momentum. This is the form of the Navier-Stokes equation, except in this case it's compressible Navier-Stokes. And this is actually just a different way of casting Newton's second law, mass times acceleration. This is the sum of the forces. So on the left-hand side here, rho, that relates to mass per unit volume. This is the acceleration if you're in an Eulerian coordinate system. And then the sum of the forces, we have gradients of pressure, being pressure forces. I have viscous forces here associated with shear viscosity, and then a second viscosity here associated with the bulk viscosity. And again, if you've seen the standard incompressible Navier-Stokes equations, for incompressible flow, the divergence of the velocity field vanishes. This term goes away, and you'd only have this term for the incompressible Navier-Stokes. But for acoustics, we need to have all of them. So if you look at these equations, the unknowns that are present is rho, pressure, and 3 velocities. So I've got 5 unknowns. But I've actually only got 4 equations, continuity, and then momentum equation, which actually has 3 equations because it's in the X, Y, and Z coordinates if you're in Cartesian coordinates. So we need to get extra equations to be able to close this off. Typically, we use an equation of state, which allows us to say how different thermodynamic properties are related to each other. Now, for simple compressible fluids like water, you need to know 2 things about a fluid, 2 independent things about a fluid to know everything else about it. And so the equation of state is typically the pressure can be expanded in terms of the density and the entropy. So we've added another equation, but we've also added another unknown. So we need to add some more thermodynamics to get closure on this. And so, for example, if we look at the rate of change of entropy, we can relate it to heat flow. And then with a little bit of extra thermodynamics on that, we can get a set of closed equations. So these are the basic underlying fluid dynamics equations. Right now, they're in their most general form. If we want to do the acoustics problem, then what we make is what's referred to as the acoustic assumption. So we're going to say that the total pressure P is the ambient pressure plus a small fluctuation with a lowercase p, which is associated with the sound wave. Similarly, for the density, it is the ambient density rho naught plus a small fluctuation in the density, which I'll call rho prime. And then the particle velocity u, I'll assume here that there's no net flow. So we just have, all the particle velocity is going to be associated with the acoustic wave. So if I put these assumptions into those equations and just take the linear terms and do some manipulation on that, then you get to the linear lossless wave equation. So I've made assumption linear acoustics and we've neglected the losses. And I won't go through the algebra there. If you look at a standard acoustics textbook, you can find it. And so we have the Laplace operator grad squared acting on P. So that's the three-dimensional second order differential operator. And the time derivative equals 0 is our linear lossless wave equation. It's similar to wave equations you would have seen in many other fields. This is in 3D. It turns out for one-dimensional problems, so for example, if we say the pressure varies only with only x variable in space, doesn't have any y or z dependence, then we get an exact solution. It's referred to as D'Alembert's solution. So for one-dimensional propagation, then the pressure as a function of x and t has this form f with an argument t minus x over c, and then g with an argument t plus x over c. And this is a general solution that solves the one-dimensional wave equation. And the two terms in here have a physical interpretation. The f of t minus x over c, that corresponds to a plane wave moving in the plus x direction, often referred to that as a right traveling wave. And the g form with the t plus x over c as its argument corresponds to a plane wave that's traveling in the left direction or moving in the negative x direction. And this is a general solution. F and G you can get either by knowing initial conditions or having a boundary, if you know what the boundary values are. And so they can be any function. And so I just want to make the point that the waveform that solves the wave equation can be any shape. It doesn't need to be sinusoids. Sinusoids have some very nice properties, but actually as long as they're smooth and well behaved and you can take derivatives, then they will satisfy the wave equation where you just have this argument either t minus x over c to go to the right or t plus x over c to go to the left. Now for biomedical ultrasound, and we'll make use of this, so the one-dimensional wave solutions have some, make so a lot of the algebra simpler. And in biomedical ultrasound, where we typically send beams of sound into the body, it's almost one-dimensional. We can actually gain a lot of insight by looking at one-dimensional propagation. So in the case where we have one-wave propagation, what's referred to as a plane progressive wave, so I have a one-dimensional wave moving through a medium, and that's often referred to as a right traveling or a forward progressive wave. Then the pressure as a function of time and space has this functional form f of t minus x over c naught, where f would be the function that the source has got. At x equals 0, it would be the time dependence of the source that would be driving the pressure wave. As I mentioned, when we have acoustic wave, we have perturbations in pressure, but also in density and in the particle velocity. And we can work those out by using this in terms of the other fluid mechanics equations. So the particle velocity we can get by putting this into the momentum equation. So the linear momentum equation takes this form here. So if I put this form into here and do some differentiation in one integration, then you get that the particle velocity is the pressure divided by rho naught c naught. So the particle velocity is actually in phase with the pressure, and it's just scaled by this product of rho naught and c naught, where rho naught is the density and c naught is the speed of sound. And the density fluctuation, if you go to the equation of state, turns out the density fluctuation rho prime is equal to p over c naught squared. So again, it also is in phase with the pressure. Now one of the properties that turns out to be useful to when we do acoustics is what's referred to as the acoustic impedance, or to be technically correct, the specific acoustic impedance. So the specific acoustic impedance Z is defined as the pressure divided by the particle velocity. This is analogous to electrical circuit impedance, where the impedance is the voltage over the current. So the voltage is the pushing, does the pushing, and the current is the flow. And in acoustics, it's P is our pushing variable and U is our flow variable. Now, in general, for general sound waves, P over U can be a complex function, just like it can be for electrical circuit theory. But when we have a forward progressive plane wave, if we put this expression in here, U into here, pressures cancel out, and we find actually that the specific acoustic impedance Z is rho naught times C naught. And that's actually a material property. It doesn't depend on the wave. And this product, rho naught C naught, is referred to as the characteristic impedance of the material. And for plane progressive waves, what allows us to move quickly between the particle velocity and the pressure. And then just for when we start looking at reflection, what will be interesting is we also need to consider some cases of left traveling wave. So if you remember, for a left traveling wave, it has this functional form of T plus X over C in the argument. If you put that into the momentum equation, then you find that U is actually equal to minus P over rho naught C naught. So there's a negative sign in there. And that's for as the wave travels left, for a positive pressure, the particle velocity is going to be in the negative direction. And so you've got to have a negative particle velocity associated with it. The density fluctuation doesn't change. It stays the same sign as the pressure. But just to keep that in mind, that when you have a negative going wave, a left traveling wave, the particle velocity is out of phase with respect to pressure. For right traveling waves, everything is in phase. And then the last bit of variable we need that's associated with this is to understand the power. And again, we make analogy to electric circuit theory. If you remember, for electric circuit theory, the power deposited in a component is the voltage times the current. And for acoustics, it's the pressure times the particle velocity. We tend not to do power itself, but we do the power per unit area, which is referred to as intensity. And so it's got yacht units of watts per meter squared in SI units. And so the way we get it, we take pressure times particle velocity, we integrate over some integration time, TA, and then we take the average of this, so we divide by 1 over TA to average out the time we've integrated over. And this averaging time TA, if we have a wave like a sine wave, then it would be the period. If you've got a short pulse, it will be the duration of the pulse. But for most of what we're going to talk about here, it will be just the period of a sine wave. So if you've got a plane progressive wave where we know that U is P over rho naught C naught or P over Z, then if we put the algebra into there, then we find that the intensity is the RMS pressure squared divided by the impedance for a plane progressive wave. And that actually works for any waveform shape. If you know you have a sine wave, then the RMS pressure is the amplitude of the wave divided by the square root of 2. And so the intensity then goes as the pressure amplitude squared divided by 2 times the impedance. And again, to just put some sort of typical numbers in for what we get in biomedical ultrasound, particularly in therapeutic ultrasound, we're on the order of megapascal pressures. And so 1 megapascal of pressure corresponds to about 30 watts per centimeter squared. And we often refer to intensity in acoustics with watts per centimeter squared so that we get numbers that are sort of without too many zeros on them. Notice that the intensity goes as the pressure squared. And so if we double the pressure from 1 to 2 megapascals, I get 4 times the increase in intensity. So at 2 megapascals, you have about 120 watts per centimeter squared. Right. So those are sort of some typical values. As I mentioned before, the speed of sound in tissue is about 1,500 meters a second, about the same as water. But if we look perhaps a little bit more closely at some of the details, this is a table that gives you some rough values for speed of sound and impedance. And those, so first approximation, those are the 2 most important material properties. Some of the others will play a role later on, but sound speed and impedance are the first 2 that are the most important to begin with. So for water, the actual speed of sound in pure water at room temperature is about 1,480 meters a second. It's got a density of 1,000, so the impedance is 1.48 by 10 to the 6 rails. And then if we look at other soft tissue, they all have densities on the order of 1,000. They're not so different from water. And their sound speeds are typically a bit higher than that in water. So 1,570 for blood, 1,550 for liver, 1,560 for kidney, 1,580 for muscle. And these are rough values, so within about 10 meters a second. If you look in the literature, you'll find a range of values. So these are sort of in the mid-range of what you might get for biological variability. The one to jump out with respect to soft tissue is fat, which has a sound speed more like 1,450 meters per second. Okay. So a typical average, if you take a human being and you average out all the different organs, all the soft tissue organs, and the average sound speed is about 1,540 meters a second. And this is a value that's used quite generically now in the literature. Most ultrasound imaging systems assume that the speed of sound in soft tissue is 1,540 meters a second. And it's how most imaging systems use time of flight measurements to back out what the distance is by using that value. Now, 2 cases where the sound speed is quite different from what we get in soft tissue. So one is the dense bone. So that's the cortical bone in your body, which has a sound speed in excess of 4,000 meters per second. Also a higher density. So it's got an impedance quite a bit higher than you'd have for soft tissue. And the second one, air. So for example, air in the lungs or gas bodies in the gut. So the speed of sound in air is about 340 meters a second. Density is obviously almost 1,000 times less than water, so the impedance is significantly less than that you'd have for soft tissue. Right. So now let's look at what happens as we have reflection and refraction. All that stuff I've showed so far is if we've got propagation through a homogeneous medium. So if we go to an inhomogeneous medium, so if we, for example, we look at a case where we have two different media where we have an interface, then we can start to look at reflection and refraction. So I've got impedance 1 here with a density ρ1 and a sound speed c1, and so an impedance is the product of those. And we've got an incident wave coming in. Again, doesn't need to be a sine wave, so I've got a little triangular wave coming in here with an argument t minus x over c1. That's my incident wave. Hits this interface at normal incidence to begin with, and a second medium with a density ρ2 and a sound speed c2. So similar as you perhaps have seen with previously at high school, either with acoustics or with light, when we hit the interface, we get some of the wave is transmitted and some of the wave is going to be reflected. The transmitted wave has the same functional form as the incident wave, so the same triangle form, but now the argument is going to be t minus x over c2 because it's going to travel at a different sound speed. And then the amplitude will be modified by a transmission coefficient. The reflected wave will come back, and so because it's now moving as a left traveling wave, it's going to have an argument of t plus x over c1, but the same functional form, and it will be multiplied by a reflection coefficient r. At the interface, if we ensure that the pressure and the particle velocity are continuous across the interface, then it turns out you can solve for r and t. And again, those derivations are in a standard acoustics textbook, so I won't go through them here. But the reflection coefficient r turns out to be the difference in the impedances divided by the sum of the impedances. And the transmission coefficient t is twice the impedance of the second medium divided by the sum of the impedances. So these are the pressure reflection coefficients and the transmission pressure transmission coefficients, because they relate the pressures of the transmitted and reflected waves with respect to the incident wave. And if we look at some special cases, so if we consider, for example, a case where Z2 is much, much bigger than Z1, so for example, going from tissue, say, into bone, in that case there, R will be approximately unity, so you'll get most of the wave will be reflected, and the transmission variable t will be 2. So you get higher amplitude here, and you get the wave coming back with a magnitude of 1. In the second case, where Z2 is much less than Z1, so for example, that's like going from, say, tissue into air. In that case, if Z2 is small in comparison to Z1, we're going to get reflection coefficient as -1. So the reflected wave that comes back has the same amplitude as what came in, but it's been flipped upside down. So you get this phase inversion. And the transmission coefficient goes to 0. So there's no pressure in the second medium. The first case is typically referred to as a rigid interface. So it turns out that if you do the algebra, there's very little particle velocity at the interface. And then the second one, it's a pressure release interface. So the pressure vanishes at the interface and you get this negative wave coming back at you. And then in the third case, where Z2 is approximately equal to Z1, which is most interfaces inside the body as you go from one soft tissue to the next, then if Z2 is approximately equal to Z1, this is very close to 0. So we have very little reflection. And the transmission coefficient goes close to unity. And this is a case where we often refer to this as being impedance matched. And the fact that soft tissue is such that the impedances are about the same is what allows us to send ultrasound deep into the body. If everything reflected at some of the first interfaces, all that energy would come back. We wouldn't be able to send information deep. And that's why we can both do imaging as well do therapy with acoustics. Now, these are the pressure coefficients. The power or the energy that's carried by the wave is measured in terms of intensity. So if we look at those, the intensity of reflection coefficient is the intensity of the reflected wave divided by the intensity of the incident wave. If you do the algebra on that, turns out that's the magnitude of the pressure coefficient squared. So that's the difference in impedances over the sum all squared. Right, so you just need to be careful with these coefficients. They're not, the pressure coefficients and the intensity coefficients are not identical. And similarly, if you do the intensity transmission coefficient, that's the transmitted intensity over the incident energy, and do the algebra, then you get this expression here, which is not, it's not, for example, t squared. It's got some extra terms in it because as you change from one medium to the next, the impedance term changes in the intensity calculations. And what's important to notice here is if you remember from that previous slide, the pressure wasn't conserved. So T plus R for the pressure coefficients isn't conserved, but energy is conserved or intensity is conserved. So the intensity transmission coefficient and the reflection intensity coefficient always add up to 1. Energy is conserved as it should be, but pressure is not conserved. Pressure is continuous across the boundary, but it's not conserved. Okay, so what does that have? What sort of values do we get for typical propagation within the body? So what I'm showing you here is the intensity transmission coefficient going from soft tissue from one medium with soft tissue properties, so with an impedance about 1.5 megarails, into a second medium where the impedance of the second medium varies from 100 rails up to 10 million rails. And so the blue line is the intensity transmission coefficient. Up here, this is all the values that you get for soft tissue that I showed you on that first graph. And you can see the intensity transmission coefficient is very close to 1, and the pressure reflection coefficient is less than 1%. And again, that's this idea that we can get most of the wave travels through different layers of soft tissue. This red line over here shows the typical values for intensity transmission coefficient that you get going into bone. And you get somewhere on the order of 50 to 60% of the energy will actually make it into the bone. Reflection coefficients of about 0.6. And so that means we can get ultrasound into the bone, not huge amounts, but we can actually get some into the bone. So even though ultrasound waves will reflect off bone, not all that comes back at you, only about 40% comes back. Some of it will actually pass into the bone itself. And then this dot way, way, way down here, that is the intensity transmission coefficient if we go from tissue into air, right? And you can see that it's very small indeed. We get almost nothing through. And indeed, the pressure reflection coefficient, so it's minus, remember, because we're going into a softer material, 0.9995, right? So that means if you put 10,000 pascals of acoustic pressure into a wave, 5 pascals makes it into the air, but the other 9,995 come right back at you. And that's why air in the body in particular is a real problem with respect to biomedical ultrasound. You can't really get anything past it. Bone is a problem too, but you have at least a chance of getting something through the bone. But air really is a major barrier with respect to biomedical ultrasound. Okay, so those are typical values if you have normal incidence. If we go to oblique incidence, then again, you will have seen this probably in optics at high school physics. So if we have an incident wave now coming in at an angle theta I, and theta I is the angle between the ray coming in here and the normal to the surface, then when it hits that surface, it will be partially reflected, and the angle of the reflection here will obey specular reflection. So the sine of theta I and the sine of theta R must equal, so that means theta I must equal theta R. So we get specular reflection. And we also get a wave that transmits into the second medium. And again, if we match stuff at the boundary, then we find that we obey Snell's law. So the sine of theta I over C1 is the sine of theta T over C2. So this will tell us what the angle is, right? So commonly referred to as Snell's law. Snell was a Dutch scientist. In other areas, it's got different names. So Descartes in France came up with the formula at the same time as Snell. And indeed, the form of Snell's law that we use was actually first given by Descartes, from what I understand. But the understanding of the refraction predates way back. So there's some work from Persia by Ibn Sal showing a refraction going back to at least the year 1000. Then, so we have this change in angle. It also affects how much energy comes back. So we can work out the reflection coefficient, the pressure reflection coefficient when we have oblique incidence. And so the reflection coefficient, what happens is that the impedance gets modified by the cosine of the angle. So where instead of having the differences in the impedance, it's the impedance divided by the cosine of the local angle that you put in here. And then you can solve for what the reflection coefficients are. So that refraction will actually change the amplitude of the reflected wave that comes back. And cosine theta t, as we'll see in a little bit, particularly when we have specular, when we have total internal reflection, then theta t can be imaginary. But if you use this formula here to calculate cosine theta t, then you can still work out a reflection coefficient, and it will account for it being real when we have a proper reflection, and it will become an imaginary variable when we have a total internal reflection. So what is the effective reflection on the change of angle as we go from one medium to the next? So what I'm showing you here, this is theta I going from normal incidence out to 60 degrees. And then this is the difference between theta T and theta I. So this is how much the beam is, or the ray diverges from its initial angle or its incident angle when it goes on. I'm doing this for a range of ratios of sound speed from starting here where the second medium is 10% higher sound speed than the first, down to here where the second medium is 10% lower sound speed than the first. Yellow is when it's exactly 1, so theta T is equal to theta I. There's no difference, doesn't change direction because the sound speeds don't change. But as we go across to different angles, then as we increase the angle in, the refraction gets stronger, and the ray will bend off by more and more amounts as we come at more oblique angles. The dashed lines here show when the divergence equals 2 degrees. And I put that value in because if you have a 2-degree change in angle, if you go out 10 centimeters, so that's sort of a typical depth that we might focus to in the body, then that corresponds to a 3-millimeter offset, right? When that's sort of the accuracy which we'd like to be able to predict that. So those dashed lines sort of give a rough idea of where you'd be able to get within a few millimeters accuracy by neglecting refraction. And so what you can see, it depends on how much the speed of sound changes, and also what angle you're at. But somewhere between about 20 and 30 degrees is where you'll start. If the angle is greater than that, you will not be able to predict accuracy to within a few millimeters. Right? And that can play a role in treatments. This is actually some data from a clinical trial that was done at the University of Oxford a few years ago, where they were trying to treat renal carcinoma. And this is an MRI after the treatment. This is the kidney here. Therapeutic ultrasound transducer was placed here, and they were trying to focus in onto the kidney. That's where they wanted to do the treatment. You can actually see there was a disruption here of the perirenal fat. And one possible explanation for seeing this disruption of the perirenal fat is because the fat has a different sound speed, you've got refraction, and so the sound, rather than being delivered to the location that was desired, actually ended up coming a little bit in front of the transducer because of this refraction effect. Right, and then, as I mentioned, we have total internal reflection in acoustics, similar as you've perhaps seen in optics. And so this happens where you go from one medium into a medium that has a higher sound speed. And the critical angle is such that the sine of the critical angle is the ratio of C1 to C2. And once your incident angle exceeds the critical angle, no energy actually makes it into the second medium. It all comes back in that reflected wave that returns back to you. All right, and so here's a little movie that just shows an example of incident and reflected waves as we go through different angles beyond the critical angle. So here's the incident wave coming in here. This is for an incident angle of 10 degrees. Here's the interface, and you can see in the second medium, now it's been bent just a little bit further over. It's got a higher amplitude because the transmission coefficient in this case is greater than 1. So if we play this movie, I'm going to change the angle. So you can see I'm increasing the angle here. And as we increase the incident angle, the transmitted angle is getting stronger and stronger. And as I approach 30 degrees, which is the critical angle in this case here, becomes vertical. And then beyond that, we get this exponential decay in the second medium. And that's because at this point, the angle theta T in the second medium actually becomes complex. And so you can work that out with respect to reflection coefficient. It gives us a complex reflection coefficient. And we get this decay in the second medium, which follows an exponential decay. The scale on here on the horizontal axis is actually in terms of wavelengths. And so you can see that once we get beyond the critical angle, there is a little bit of a disturbance still in here. It's what's referred to as an evanescent wave. It's not actually a wave. It doesn't kind of propagate in the way a wave does. It just exponentially decays. But it's trapped within about one wavelength. So you get a little bit of disturbance to make sure you match the boundary condition, but it's all trapped within one wavelength. Right, and so cases where this might happen inside the body. So for example, if you have a cortical bone, so for example, if you look like at a rib, if we're doing therapeutic ultrasound, you can see for this rib, this is a CT of the rib. The white here is the cortical shell on the outside of the rib, and then we have the spongy cancellous bone in the middle. The speed of sound on this cortical bone is about 4,000 meters a second. And so the critical angle between water or soft tissue and that cortical bone is about 22 degrees. So if you have sound coming in because of the shape of the rib, some sound will be normal, but there'll be some sound that'll be beyond critical angle, and that sound won't enter into the rib. It will do total internal reflection in soft tissue and remain on. So to recap what I've given in this first short lecture, acoustic waves are perturbations that exist in the pressure, density, and particle velocity of the underlying medium. Sound waves can be any waveform. We often talk about them in terms of sine waves, but they don't need to be sine waves. They can take any particular waveform. When we have plane progressive waves, then the pressure, density, and particle velocity are all in phase, and they're related by the material properties, either rho naught C naught for the particle velocity or the Sauter speed squared for the density fluctuations. The specific acoustic impedance, which is the ratio of the pressure to the particle velocity, for a plane progressive wave, turns out to be the same as the characteristic impedance of the medium, which is the product of rho times C naught. We typically measure energy in terms of intensity for acoustics, which has units of watts per meter squared, and that's proportional to the pressure squared. So doubling the pressure really relates to a 4-time increase in the amount of power. When we go from one medium to the next, we get reflection. And remember, energy is conserved as we undergo a reflection, but pressure does not need to be. So as we go from, for example, a soft medium into a hard medium, the pressure in the hard medium can actually be twice the incident pressure that you put in. And we get, as we go from one medium to the next at oblique angles, we get refraction, where the sound of where the wave speed will change in different directions. And when we go beyond the critical angle, we can get total internal reflection. And that particularly would happen if we're going from soft tissue into a bone. So that's the end of this first ThUNDDAR Live talk on ultrasound propagation and the fundamentals. Thank you very much for your attention.